The next session that we are going to learn is the quadrupole effect in Mosfet spectroscopy. Okay, majority of these Mosfet spectrum will have a non-zero spin. Okay, that is the first thing that we have to understand. Majority of the Mosfet nuclei will have a non-zero spin, and out of that, most of them will have half integral spins. Most will have half integral spins. Half integral spins. Okay, so we will be considering some nuclei, some most bar nuclei having half integral spin. That is because that is the most common case. And there is a selection rule which states that the spin of the spin of the ground state nucleus should be different from the spin of the excited state nucleus. Okay, so if you consider that the ground state spin is half, that's the lowest possible half integral spin. That is, the ground state spin is equal to half. Then, according to the selection rule, the excited state spin should be greater than half. If we are considering only half integral spins, it should be at least 3 by 2, right? And reverse also we can think, if the excited state nucleus spin is equal to half, then the ground state nucleus spin should be at least 3 by 2 in majority of the cases. Okay, so we are considering a nucleus like this, that is iron 57. That is the most studied nucleus in the Mosfet spectroscopy, iron 57 nucleus. And in the case of iron 57, the spin of the ground state is equal to half, and the spin of the excited state is equal to 3 by 2. Okay, so you already know that if the spin is half, then that nucleus can orient in two possible directions in an electric field. Okay, so the spin half nucleus, S is equal to half nucleus, will have two orientation. Okay, like this and like this. And if this is an electric field is in this direction, then it will have two orientations like this. It will align with the field and at certain angles. Okay, and both these angles will be same. Okay, both the angles will be same, and this corresponds to I is equal to minus half, and this corresponds to I is equal to plus half. You already know these things because you already learned NMR spectroscopy. Okay, there we are talking about magnetic field instead of electric field. That's all. So this is the fate of the nucleus in an electric field if its spin is half. And if the spin is equal to 3 by 2, as in the case of the excited nucleus, then it will have four orientations, right? How many orientations will depend upon the 2s plus 1 value, 2s plus 1. In the case of half, 2s plus 1 is equal to 2s plus 1 in the case of half is equal to 2 into half plus 1, that is equal to 2. Okay, and 2s plus 1 in the case of 3 by 2 is equal to 2 into 3 by 2 plus 1, that is equal to 4. Therefore, four orientations are possible. If this is the electric field, then it will have four possible orientations. Okay, one will be like this, another one will be like this, another one will be like this, and the one will be like this. Okay, four orientations are possible, and this corresponds to I is equal to minus 3 by 2, and this corresponds to I is equal to minus half, and this corresponds to I is equal to plus half, and this corresponds to I is equal to plus 3 by 2. So four orientations are possible, and this angle are same, and this angle, okay, this angle and this angle are also same. Okay, so this is the fate of the spin 3 by 2 nucleus in an electric field. So if you are considering the energy of these spins, the nuclear energy in the electric field, that depends upon the angle. Since in the case of the plus half nucleus, spin is equal to half nucleus, then in this case both orientations are at the same angle from the electric field gradient. Therefore, both these orientations will have the same energy. Okay, both these orientations will have the same energy. So let me draw that here. Both orientations will have the same energy. So this corresponds to I is equal to I I is equal to plus half, that is of the ground state, and this is of the I is equal to 3 by 2. This corresponds to the excited state. Okay, excited state energy will be greater than the ground state, and at the ground state, even if there is an electric field, both orientations will have the same energy. Therefore, since it has the same energy, it will have only one energy state. Okay, both plus half and minus half states will have the same energy. But in the case of spin is equal to 3 by 2 case, there are two angles, right? Even if there are four orientations, only two angles are there. So these two, that is I is equal to minus 3 by 2 and I is equal to plus 3 by 2, both of them will have the same energy. And I is equal to plus 1 by 2 and I is equal to minus 1 by 2 will have another energy. So in this case, the energy will be split. Okay, it will be split, and two energy levels will be possible there. One energy is this one, that corresponds to I is equal to plus or minus half, and uh, this corresponds to I is equal to plus or minus 3 by 2, plus or minus 3 by 2. Okay, so these are the energy levels for the excited state and the ground state nuclei. So if you are considering the transitions from here, how many transitions are possible from here? So one possible transition is this one. See, from here to here, one transition is possible. This one. This is one possible transition. And another possible transition is this one. Okay. So these are the two possible transitions from the between the excited state and ground state. So when the nucleus is formed in the excited state first, then it comes to the ground state, then the gamma ray will be emitted, and this will be absorbed by the sample nucleus in the ground state, and that sample nucleus can make these two transitions. Okay, so corresponding to these two transitions, we will get two bands in the Mosfet spectrum. So if you are considering the Mosfet spectrum of the iron nucleus in an electric field, then we should see two bands like this. Okay, instead of seeing one, we should see two like this. Okay, so this is what we can see. Actually, what we have to understand here is that I was talking about an electric field. It can be an external electric field, but it is not necessary that it should be an electric field. The inside the molecule itself there is an electric field, and that electric field is sufficient to bring this type of effect. Okay, and for example, we can consider the Mosfet spectrum of FeCN 5 times FeCN 5 times um, NO, FeCN 5 times NO. Okay, and in this case, in the case of the FeCN 5 times NO, in this case, we can see that there are five CN groups and there is one NO group. So, what will happen? This is not symmetrical. Okay, if there were six CN ligands, it would be completely symmetrical around the iron. Then there will be no net electric field. Since it is not symmetrical, since there are only five CN ligands and one NO ligand, then the electric field is not symmetrical here. So it will create a net electric field gradient, and therefore this effect can be seen in this compound even without applying an external electric field. So if you are taking the Mosfet spectrum of this compound, then you will see a spectrum like this. Okay, when we are drawing the Mosfet spectrum, in this axis we have millimeter per second, millimeter per second, and here we have counts per second. counts per second. And if you are checking this Mosfet spectrum, it will be like this. The zero is where here. Okay, the Mosfet spectrum like this. There will be one peak before zero, and just after zero there will be another peak. Okay, so actually the two bands. So this will be the Mosfet spectrum of the this FEC and 5 times NO2 minus. Okay, so now you understood why the Mosfet spectrum is like this. But if you are checking the Mosfet spectrum of FEC and 6 times 4 minus, FEC and 6 times 4 minus, FECN 6 times 4 minus, this we already considered. There you can see that the ligand field is highly symmetric. So there will be no net electric field gradient. So this type of an effect will not be there. So if you are checking the Mosfet spectrum of this one, as we already saw in the last class, the Mosfet spectrum will be like this. Okay, the zero is somewhere here, is millimeter per second. Okay, and you will see a Mosfet spectrum like this, and it will come somewhere in the minus half millimeter per second. Okay, you will see only one band in the Mosfet spectrum. Okay, so now you understood why, how an electric field is causing the quadrupole effect, and this is called a quadrupole effect because one of these nuclei is uh, having the spin plus or minus 3 by 2. Therefore, it will be split. It can have four orientations, and corresponding to four orientations, there will be two energy states, and therefore there will be a splitting of the Mosfet peak. Okay, so this is what is happening in the electric field. Now we can check what is happening in a magnetic field, for example. Okay, if in a magnetic field also you know that these nuclei will have a splitting in the magnetic field, means each orientation will have a different energy in the magnetic field. It is unlike the electric field. In electric field, plus or minus half will have the same energy, and plus or minus 3 by 2 will have the same energy, but it is not the case in the magnetic field. In the case of the magnetic field, minus half will have one energy, plus half will have one energy, minus 3 by 2 will have one energy, and plus 3 by 2 will also will have one energy. So the pattern will be much more detailed in the case of a magnetic field. So if you are considering the magnetic field here, let us consider the ground state, that is a ground state ion Fe. Okay, this is a ground state ion, and here we are considering the excited state ion, Fe star. This is excited state, and excited ground state ion has the spin half, and excited state ion has the spin 3 by 2. Therefore, the ground state ion will have two orientations. Okay, and the orientations are corresponding to IC is equal to plus half and IC is equal to minus half. Here we have to consider that in the case of the ground state, okay, in the ground state, um, the G value will be positive, but in the excited state, G is negative. So G is positive in this case, positive, and in this case, G is equal to negative. Okay, what is this G? You may be remembering. It is, you already learned in NMR spectroscopy that the splitting of the energy, or the spacing between the energy levels delta E is equal to uh, G beta N V Z divided by H. You already know this, right? Here, this is nuclear G factor, this is nuclear magnetone, BZ is applied field, H is a Planck's constant. So this is nuclear G factor. The nuclear G factor may have opposite sign. That is possible. The opposite signs in the ground state and excited state. In the case of iron, it is there. In the case of iron, G is positive in the ground state and G is negative in the excited state. So depending upon the G, uh, the sign of the G determines which IZ value will have uh, greater energy and which Iz value will have a higher energy. Okay, since G value is positive in the ground state, the splitting will be like this. Means this will have I is equal to plus half will have lower energy, plus half will have a lower energy, and I is equal to minus half will have a lower energy. You have already seen this in the case of the proton NMR, right? In the case of the proton NMR also, proton has a G value positive. So you also saw that plus half orientation have a lower energy and minus half orientation have higher energy. So same is the case here in the ground state of the ion. But in the excited state, the G is negative. Therefore, in this case, the lower energy states will have a minus sign. I is equal to minus. So the I is this state I is equal to minus 3 by 2. Minus 3 by 2 will have a lowest energy. Then comes I is equal to minus 1 by 2. Okay, then comes I is equal to plus 1 by 2, plus 1 by 2, and then comes I is equal to plus 3 by 2. Okay, see here it is different. Here the plus have lower energy, here minus have the lower energy. So this is because of the G values. So this is the situation in the case of the ion. And now each of them will have each. Now we know that in the case of the ion there are 6 energy levels altogether, right? The ground state have 2 energy levels and excited state have 4 energy levels. So if you are considering the transition from here to here, okay, which are the allowed transitions? There is a selection rule corresponding to that. The selection rule is that I delta I is it delta I is it is equal to, okay, I z is these values. These values are called I z. All these values are I z values. Delta I z is equal to 0 or plus or minus 1, plus or minus 1. These are the possible transitions. Okay, so we can consider which are the possible transitions from here. Let us consider from I is equal to minus half. We will consider the transition from here. I is equal to minus half. Okay, the first possible transition is minus half to minus 3 by 2. Minus half to minus 3 by 2. What is this transition? From minus half to minus 3 by 2, Iz is equal to minus 1. Okay, this is Iz is equal to minus 1. Iz is equal to minus 1. And now we can consider the next transition. That is from minus half to minus half. Minus half to minus half. Minus half to minus half. What is the delta iz? Delta iz is equal to 0 in this case. Minus half to minus half. And next transition is from I is equal to minus half to I is equal to plus half. I is equal to minus half to I is equal to plus half. This is the next possible transition. Okay. So this corresponds to minus half to plus half. So that is I is equal to plus 1. So we considered 3 transitions. First one, delta I is equal to this one, minus half to minus 3 by 2. This is corresponding to minus 1. This corresponds to 0 and this corresponds to plus 1. Okay. Now we can consider the transitions from this state. I is equal to plus half state. So first let us consider the transition from I is equal to plus half to I is equal to minus half. I is equal to plus half to I is equal to minus half. Okay, I is equal to plus half to I is equal to minus half. So what is the delta I is in this case? I is equal to plus half to I is equal to minus half, that is minus 1. And the next transition is I is equal to plus half to I is equal to plus half. I is equal to plus half to I is equal to plus half. So in this case, delta I is equal to 0. It is between plus half and plus half. And the next possibly is I is equal to plus half. I is equal to plus half to I is equal to plus 3 by 2, and in this case delta I is equal to plus 1. So these are corresponding to -1, 0, +1. Okay, so all the transitions allowed by the selection rules have been considered here. Now, what we are going to consider, we are going to make these transitions into pairs. Okay, let me make into pairs. The first pair is 3 by 2, 1 by 2. Okay, 3 by 2, 1 by 2. That is, I am writing excited state first. I am writing a pair 3 by 2, 1 by 2 transition. 3 by 2, 1 by 2 transition, which is that excited state. I am writing excited state. If you are seeing a pair, the first one shows the IZ value of the excited state. The second one shows the IZ value of the ground state. So 3 by 2, 1 by 2 transition is this one, right? This one, the first one. This is 3 by 2, 1 by 2 transition. The second pair is 3 by 2, 1 by 2 transition. Okay, 3 by 2, 1 by 2 transition, and then I am considering the then -3 by 2, -3 by 2, then between -1 by 2. Okay, then only it will be a pair of transitions. Okay, I am considering 3 pair like that. -3 by 2, then -1 by 2, -1 divided by 2. Which are these? Okay, I will show which are these. The first one was this one. Okay, the this transition, and the second one, that is -3 by 2, -1 by 2, is this one. -3 by 2, -1 by 2 is this one. So I picked the transition, the last one and first one. Okay, you can remember like that. And the second pair is 1 by 2, 1 by 2, 1 by 2, 1 by 2, 1 by 2. Okay, and the next member is -1 by 2, -1 by 2, -1 by 2, -1 by 2. Okay, which are these? 1 by 2, 1 by 2. The first one shows the excited state. The second one shows the ground state. So 1 by 2, 1 by 2 is this one. 1 by 2, 1 by 2. Okay, this one. So let me mark it. This is 1 by 2, 1 by 2. And -1 by 2, -1 by 2. And this is this one. -1 by 2, -1 by 2. Okay. So I picked these two. Just right to this, just left to this, and just right to this. Okay, and the third pair is this one. Now you can write the third pair itself, which is the third pair: -1 by 2, -1 by 2, +1 by 2, +1 by 2, and +1 by 2, -1 by 2, +1 by 2, -1 by 2. Which are these? Okay, let me mark it. -1 by 2, +1 by 2. It is this one. -1 by 2, +1 by 2. Okay, and then +1 by 2, -1 by 2. It is this one. +1 by 2, -1 by 2. Okay, so we have picked all these possible transitions into 3 pairs. Okay, now if we are looking into the probability of these transitions, the calculations shows that the two members in each pair, okay, two members in each pair will have the same probability. Means if you are taking the first pair, both members will have the same probability. Means this transition and this transition, okay, these two transitions, this transition and this transition will have the same probability. And if you are considering the second pair, then both members will have the same probability. It means that this transition and this transition will also have the same probability. And if you are considering the third pair, then this transition and these transitions will have the same probability. Okay, so two members in each pair will have the same probability. Now, if you are considering the relative probabilities of these three pairs, relative probabilities of these three pairs, and the relative probabilities are 3 is to 2 is to 1 for pair 1 is to 2 is to 3. Okay, so if you are taking the relative probability of the pairs as a whole, okay, then the ratio is 3 is to 2 is to 1 for 1 is to 2 is to 3. Means for the first pair, the probability is 3 times the probability of the third pair, and the second pair will have the probability of 2 times than the probability of the third pair. Okay, that is what we can understand here. Means if we are considering the probability of the third pair as 1, the third pair as 1, which is the third pair, the middle one, the third pair as 1, then the probability of the second pair, means this one and this one, will be 2, and the probability of this one and this one will be 3. Okay, that is what we can understand. So how the spectrum will appear? If we are taking the spectrum, Mosfet spectrum, it will be like this, right? It will be like this. Means corresponding to these 6 transitions, it will be like this. The first transition will have the maximum probability. Okay, the first one, because that comes in the it is that is the pair 1, right? Pair 1. So pair 1 have the possibility of 3, probability 3, so it will have maximum transition. Then the second one comes from pair 2. The pair 2 will not have that much possibility, so it comes like this. The third one comes from pair 3. Pair 3 have a least possibility, only 1, so this will be in the 3 is to 2 is to 1 ratio. So now we are again considering the other members of the pairs, right? So it will be like this, because this comes from the the third pair, and this comes from the second pair, and this comes from the first pair. Okay, so it will be symmetric like this. So the Mössbauer spectrum will be like this. So this is 3 and this is also 3, 2, 2, 1, 1. It will be like this. So now you understood why we are getting 6 peaks, 6 bands in the Mosfet spectrum when we are conducting the experiment in a magnetic field, and why this intensity pattern is in this way, in a very symmetric way. Okay, so this is explained by the quadrupole effect of the excited ion nucleus. So from here we can understand that the spin of the nuclei are very important, and especially if there is a quadrupole nucleus, then the pattern is going to be dramatically changed in the case of the Mosfet spectrum. And here also we have to consider that the magnetic field, we don't need to apply an external magnetic field to observe these kinds of effect. Even internal effect is sufficient enough to this to make this kind of splittings. Okay, and if we are calculate the internal magnetic field from this Mosfet spectrum, it will come around 20 to 50 Tesla. Okay, 20 to 50 Tesla. It is very large compared to the external magnetic field that we are applying in the NMR spectroscopy. In the NMR spectroscopy, we will be applying something like up to 20 Tesla. Okay, so the field inside the field inside the molecule near the nucleus, due to the internal effect, is very large compared to the superconducting field that we are superconducting magnetic field that we are applying there. But you have to remember that this field is not extending to a wide range. This is highly localized, and this field can be seen only in the vicinity of the nucleus, and this is because of the interaction between the nucleus and the electron. Okay, so this is what we have to learn about the quadrupole effect in the Mosfet spectroscopy. I hope you understood these things. If you have any doubt, please don't hesitate to ask me. And thank you for watching this video, and stay tuned.